EIR students, we have to finish lecture 16, so we're actually now lecture 17, but as I mentioned at the end of the last lecture, there's just one more example I'd like to do with regard to chapter 11.2, where we looked at average and instantaneous power. So we've got practice problem 11.4 on the board, two AC sources, 40 volts, 20 angle 90 degrees, minus J2, capacitor, inductor, plus J4, and a resistor. And what they want is for us to go and calculate the power absorbed, in other words, P equals plus VI for all these elements. Okay, so to calculate the power absorbed by an element, you need to know two things: the voltage across it and the current through it. Voltage across, current through it. So we will have to go and calculate the current through the 40 volts and the 20 volts and the 8. And what about the capacitor and the inductor? Can you remember from last time how much active or real or average power is consumed by an inductor and a capacitor? Zero, hey? Nothing. So you don't have to go and calculate anything for these two, but we still need the current through these two elements, and we'll need the current through the 20 volt source in order to calculate that power. So let's start with where we want to end. So let's say, for example, P for the 40 is going to be, so the current, we'll have to choose a current direction now. So let's make this one go in this direction, and we'll make this current in that direction. So the current goes into the minus, so we're following the passive sign convention. So because we're calculating the power absorbed, we're going to see the current goes in, so let's call that I1 squared. Not man, we're busy with a VI here, sorry. My head is in the next part of the chapter already. So it's going to be minus VI. But remember now, with the next section we're actually going to do, it's going to look a little bit different. So remember the half. Right, the half VI in there. And then the V is the VM and IM, the amplitudes of the voltage in the signal. So at this stage, and this is a bit where chapter 11 is confusing. Chapter 9, 10 and the first part of chapter 11, when we write it in phasor format, these coefficients are still amplitudes. But in our next lecture, we're going to move from amplitude to a root mean square, an RMS value. So I'm just planting the seed so long because this equation is going to change a little bit later on. All right, half VMIM, but then there is still something missing when calculating power, and that is your cosine part. And I just want to make sure, yes, I did. Cosine theta V minus theta I. All right, so that gives you the average power that goes through the 40, which means the VM we have, it's 40 volts. It's the IM that we're looking for, and this IM is the current flowing through the source. So let's call this loop number 1, and we'll call this loop number 2, and we will solve for those two currents. So this will become I1. All right, but this is the equation that we need to work through so that I realize I'm going to need this current information. Okay, so how would you solve for these two current values? Well, it's currents that you're looking for, so mesh analysis will directly give you the current value. But of course, you could have done a node analysis method there, and then this voltage minus that voltage divided by the 8 would also give you that current. And I'm thinking, gee, you know what, that would be one equation, and we're going to solve two equations now. But either way, let's stick with the mesh analysis. Otherwise, I have to redo my notes. But perhaps go and solve, make this your reference node over there, and then make that a V, I don't care, VA. Solve for VA, and then Ohm's law gives you that current, and Ohm's law will give you that current. So one unknown gives you both currents. But okay, I see I've done a mesh analysis over here, so let's stick with what I've done. So mesh 1, which is this one. So we're starting in the minus, so it's going to be minus 40. I'm not going to spare the room for the 0 degrees. Don't have that need to write that. Then plus the 1 goes through the 8, so it's 8 times I1 plus, and then we're moving through the capacitor, which is a minus J2, and then what's flowing through it? I1 minus I2. I1 minus I2, all of that equals 0. Right, so we've got a, this constant is going to go to the other side. Let's look for all the I1s. There's a 8, there's a minus J2, so it's 8 minus J2, I1. I2's minus gives me a plus, so it's a plus J2, I2 equals, and then the minus 40 goes over, gives me equation number 1. Right, that's pretty straightforward. Right, mesh number 2. Mesh number 2. Let's start with some of the capacitor. So there I've got again the minus J2 capacitor, but now it becomes I2 minus I1 because I'm in the other loop. Then plus, we're going through the J4, and it's only I2 that flows through the inductor. And then we're entering the positive of that 20, so it's plus 20 angle 90 degrees must equal 0. Right, I1s, only this one, J2, I1. I2s, I've got a J4 there, minus a J2 over there, so it's going to be plus J2, I2, really, J4 minus J2, yeah. Okay, and then equals minus 20 angle 90 degrees if we take that over. Let's simplify this one. Let's divide straight through by J2. I wonder if I did that there as well. Yes, I did. So if we now divide this by J2, what do I get? I get I1 plus I2 must equal, and remember a J is 90 degrees. So if I divide this now by 2 angle 90 degrees, so this would be the, you're not going to see there, this would be the equivalent of dividing by 2 angle, 290 degrees. So the minus 20 divided by the 2 gives me a minus 10, and the 90 minus 90 gives me a 0, so this just ends up to be minus 10, and we make this our equation number 2. Right, so that's a nice, like a simple equation. Okay, now we need to go and solve. I just want to see which one did I solve for. Yeah, let's go and subtract some. Oh yeah, you know why I didn't do this initially? So now you could go and say I2 equals minus 10 minus I1. But I notice now from this equation, you've got a J2 I2 there and a J2 I2. So, you know what, let's just simply subtract. Before we simplify, instead of simplifying, let's make this equation 2. And we're going to subtract which one from which one? 1 minus 2. Yeah. So let's do 1 minus 2. So then we've got this minus this. So we've got 8 minus J2 minus another J2. So that gives me an 8 minus J4 I1. J2 I2, J2 I2. So they just cancel out. Must then equal 40 plus 20 angle 90 degrees. But I know 2090 is just plus J20, which means I1 equals, so now it's the 40 plus J20 divided by 8 minus J4, and that gives me how much? 5 angle 53.13. 5 angle 53 or 51? What did I say? 53. 53.13 degrees, and it's a current, so it's amps. Okay, so now I've got an I1 value, which is going to be my IM value. Now to get for I2, I mean, you can substitute this now into any one of these two equations. So perhaps let's say here from I1. So now let's substitute. What did I do? 3 and 2. So I made this equation number 3, and I substituted that into number 2. You see, that's where I got lazy. Either way. Okay, so this is where the I1 plus I2 equals minus 10 would have come in quite handy. So let's say from equation 2, I get I1 plus I2 equals minus 10. And hence, I2 equals minus 10 minus I1, and that equals minus 10 minus, let me just go and stand on this side, minus that 5, was it just a 5? Something, yeah, 5 angle 53.13 degrees, and you will get a 13, sorry, that's not even next to the equal sign, equals 13.6 angle minus 162.9 degrees amps. Right, so here's the one, there's the other one. Right, so that now only gives me my currents that I need to go and calculate the powers. So I'm going to clean up a little bit, and then we just keep our I1 and the I2. So here's the two currents that we've calculated. Let's now go and calculate this P40. Right, so the power absorbed by that 40 volt source is then minus a half. Oh, now that minus is gone. Minus a half. What is VM? It's the 40. What is IM? It's I1 flowing through it, so it's times 5, and then cosine. What's the angle of the voltage? It's 0 degrees, 0 minus, and then the current of the angle is a 53.13 degrees. Okay, so you punch that into your calculator, and you will get minus 60, what's it now? Minus 60 watts on the dots. All right, so there's the power absorbed. Now, don't get scared of the minus. All right, so where did the minus come from again? This is very important. Everything is very important, I know, but this is very, very important. The minus came from the fact that we're following the passive sign convention. Passive sign convention says that since the current goes into the negative, I must write minus Vm. The rest, the math will sort out. And we worked through everything, and we saw we ended up with P40 equals, it absorbs minus 60 watts. Now, if it absorbs minus 60 watts, is the same as stating that it is delivering plus 60 watts. All right, so absorbing minus 60 watts means it's delivering plus 60 watts. All right, so you see the absorb and the deliver is basically a sign difference. Okay, so there's the one element. Let's go to the 8 ohms. I think we can sort of squeeze that in here at the bottom. So P for that 8 ohms is going to be, now remember this just from school, you know the I squared R equation. So now it's going to be half IM squared times the resistance. Now what current is flowing through it? It's I1. Now this is now magnitude, hey? IM, VM, and this IM, that's just the magnitude. Perhaps we should have written it like that to be strict. All right, so we're getting a half. What was that current? 5 squared. 5 squared and the resistance is 8. So it's 4 times 25 equals 100 watts. Now let's write it there. 100 watts. Okay, so there's it for the 8 ohm resistor. Then what is P for the inductor? What did we say? 0 watts. Because an inductor can't absorb or deliver active power. The average power in an inductor, 0. Remember that nice little sine wave that moved up and down, purely inductive, purely capacitive, average 0. Go and check the video again. So for the capacitor as well, 0 watts. Okay, so that leaves me with a deficit of 40 watts. So the resistor is absorbing 40 watts. This source is providing 60 watts. Where is the remaining 40 watts going to come from? Can only come from one place, eh? This one. So we're expecting to get 40 watts. Now if you just do a balance equation, I'm not going to see which way you did it in a test in the exam. I'm not going to check whether you wrote this equation or whether you wrote that P8 plus P40 gives me 40 watts. So that's what this needs to be. I wouldn't know that. But let's go and calculate for the 20 half Vm Im cos theta V minus theta I. And let's see if we get to that 40 watts. So it's a half. What's the voltage? 20. Current, it's now I2 flowing, so it's the times 13.6. That's a 6. And then cosine of theta V for this okie is 90 degrees minus, and how am I supposed to fit that in there? Minus 162.9 degrees. Alright, so that two minuses will end up to be a plus. You do the number crunching and you will get minus 40 watts. So P delivered equals minus 60 minus 40 equals minus 100 watts. And your P absorbed equals 100 watts. So fantastic. The book's balanced, delivered equals the absorbed, and everybody is happy. Is that all I wanted to do there? Yes, P in equals P out. This is just what I wrote over there. Okay, let's go to chapter 11.3, and for this we're going to go back to the textbook. We're going to move on now to chapter 11.3 with the heading Maximum Average Power Transfer. Now let's just do a quick reboot for you guys that did it a few years ago, not for valid academic reasons. So when you did maximum power transfer back in EBN, you typically had a Thevenin equivalent voltage circuit, Thevenin voltage, Thevenin resistance, and then some load resistance. And then you had to go and determine what this load resistance must be, the value of that load resistance, to get as much of the energy that this source has into your load resistor. And then you discovered that you'll get maximum power transfer when the load resistor equals the Thevenin resistor. Right, so this is the concept that we want to look at now, but now in the context, of course, of complex impedances. So what is that going to look like? Let's just zoom in a little bit here. All right. So now instead of just having an R Thevenin, you've got a Z Thevenin. Zoom, zoom, zoom. You've got a Z Thevenin. I can go in even more. Hey, there we go. There's a Z Thevenin. So you've got an R Thevenin and X Thevenin. And you've got an R load, X load. And not just two resistors. So there's our linear circuit. The linear circuit being our Thevenin equivalent. Oh, there it is. The Thevenin equivalent circuit and our load impedance. So the same principle. Now, how do you get the maximum power transfer? Let's go and calculate what that power is that's being transferred. So to calculate the power that is consumed or in the load, you need to calculate the current that's flowing through the load. So it's V Thevenin over Z Thevenin plus ZL. So we take the Thevenin impedance, this Thevenin impedance, we get the load impedance. Right, but from equation 11 we know that the average power is half I squared, the magnitude of I squared, so straight lines magnitude, RL. So how do we get that magnitude? And then they immediately jump to V Thevenin magnitude squared, so that's fine. We just take the magnitude and then squared. But then they suddenly jump to this equation. So where does this come from? That's where I just wrote here in pencil and added it afterwards. The magnitude of I is the magnitude of the volts divided by the magnitude of the impedance. What's the magnitude of the impedance? You take the you take the square root of the resistance squared plus the imaginary component squared. But now since it is I squared, that square root then disappears. All right, and you're left with that at the bottom. Okay. Now, objective is to adjust the load parameters RL, XL so that P is the maximum. How do we do this? We set the partial derivative relative to L and relative to XL to 0. So I'm not going to go through the math. You can go through that. The bottom line of what we find is that you want your XL to be negative X Thevenin. And RL is this root that you have there. So in other words, as I said, you can go through the derivation. Here's the bottom line, that your load impedance needs to equal Thevenin resistance minus JX Thevenin. All right, not exactly the same as your Thevenin. The resistors are the same, but the reactances are opposite in sign. So they need, at the top there, they need to cancel out, so that you've got maximum current flowing, because now if the two X's cancel out, so that makes your total impedance as small as possible, and then your load resistor must equal your Thevenin resistance, which is now then back to this squared. So you effectively reduce your circuit to look like this again by having your X components cancel out. So that is Z Thevenin's conjugate. Okay, but now here comes not a boo-boo, but a catch in the textbook. They then say that this result is known as maximum average power transfer theorem and gives us a maximum average power of this. But this equation, V Thevenin magnitude squared over 8R Thevenin, only applies, listen carefully now, it only applies if your load has an X component. It only applies if the load actually has an X component. What would happen if your load was only a resistor? Then this equation no longer applies. You have to first go and calculate the current so that you get back to this equation. Right. You have to, if you have a purely resistive load, you have to calculate the power using this equation and not using this equation. Alright, so what happens, and then this is the last part, tells you, what if it is only a load resistor? In other words, XL is already 0. So in a case where the load is purely real, only resistive, and XL is 0, then your load resistance must become the magnitude of Z Thevenin. Okay, so you've got two scenarios here that I want to point out. I wonder if I'm going to write them down. Now you can go and summarize them. So scenario A is where your load impedance has got both an R and an X component. In that case, your R load must equal R Thevenin and X load must equal minus X Thevenin. Scenario B, where your load impedance ZL equals RL, 0 XLs. In that case, your RL must equal the magnitude of the Thevenin impedance, as we've got there. And then this equation 1120 does not work. What equation will always work? This one will always work. Always safe to first go and calculate that current using your Ohm's law, I suppose. Ohm's law always works. And then you get the power. All right, so that's the only little oops here I wanted to show you, that the textbook does not make all that clear. Righty, let's go and work through another practice problem. Let's work through practice problem 11.6. So this is now an example where the load resistor is just a resistance, no reactance there. So what you probably now figured out is that if you talk maximum power transfer, you're talking Thevenin equivalent circuit. So in order to calculate the maximum power that can be transferred to RL, in other words, what value must we make this load resistor so that we can get the maximum power into the load? You don't want to waste energy in your circuit. You want to get as much as possible of the energy in your source over to the load. So for that, we first need to go and get the Thevenin equivalent circuit of what the load resistor sees. So what does the load resistor see? It sees that part of the circuit. So we need to start reducing it from that direction. Okay. First, let's go and get the Thevenin impedance. That's usually the easiest, Z Thevenin. So for a Thevenin impedance, we make all the independent sources, make those as 0. So this will become a short circuit. If this is a short circuit, what does the circuit look like? Let's perhaps draw so that I'm just going to do this. So now, how is the 80 plus J60 connected to the 90 connected to the minus J30? They are all in parallel. Remember, I'm seeing this as one impedance. I'm not seeing it as two in series. Yes, it is two in series, but a real and an imaginary part gives me the single complex impedance. Well, impedance is complex by definition, but anyway, so this impedance is parallel with a 90, is parallel with a minus J30. So it's 80 plus J60, parallel with a 90, parallel with minus J30. Alright, so that you chuck into your calculator and you will get a 17.18 minus J 24.57 ohms. Now remember I said that impedances you typically write in rectangular format like we have over here, because we're interested in what the real part and what the imaginary part is. Now what we're going to do now, this scenario is probably the only exception where I'm interested in the phasor format, the polar format. Why? Because I know that RL must equal the magnitude of Z Thevenin. Where am I going to get the magnitude is by converting this into the polar format, and then you get a 29.98 angle minus, so it's more capacitive, huh? Oh yeah, there's a minus, so it's a capacitive circuit, 0.04 ohms. And here is my answer. So in other words, RL must equal, well, pretty much 30 ohms. Remember I said at least 3 significant digits in the test, so if you're going to make this at least 3 significant digits, you're going to get your 30 ohms. And remember the default tolerance. The default tolerance in the test is 1%, so this 30 ohms would be fine. Okay, now to get the actual P max value, we need to find out what the current is that's going to flux. So let's call this I load. What will that I load be? Well, I load will be, let's write here. I load is going to be V Thevenin divided by Z Thevenin plus RL. So we now know what RL is, right? So we're getting there. So let's go and get our V Thevenin next. So what about V Thevenin? I'm going to clear up space here. So this is going to be 30 ohms. Okay, so I can get get G gone. I don't want to lose that information because I'm going to need it again there. So I'm going to keep that there. And I need to put back my source now because I want to calculate V-Thevenin. I can't write V-Thevenin in the circle, simple. Plus, minus. Okay, so for the Thevenin impedance, I need to make this an open circuit and look at what is it seeing. So I'm going to redraw that circuit for V-Thevenin. So now I'm looking at the following circuit. And this, and then resistor, and what's that, capacitor. And I want to know this open circuit voltage, plus, minus. So if I take away the load, what is the voltage that I'm going to see there? And what my eye see is this. If I can combine these two into one impedance, I hope that's what I did. Yes, I did. Then I've got an impedance in series with an impedance, which means I can do a voltage division. Okay, so let's go and do that. So let's call this Z parallel equals that 90 parallel with minus J, what was it, 30? And that gives you a, oh, it's actually a nice value, 9 minus J 27 ohms. Okay, so that's Z parallel. Then I can say that V-Thevenin is going to be the source voltage. That's my Vs over there. And I'm looking for the voltage across this parallel combination. So it's Z parallel over Z parallel plus that 80 plus J60. Did I give it another name or something? No, I didn't. J60. Okay. So the Vs is 220 angle 60 degrees multiplied with, sorry, it's a bit skewed, the 9 minus J27 plus 80 plus J60, and at the top the 9 minus J27, and you crack all of that and you're going to get a 65.96 angle minus 31.9 degrees volts. In case you were wondering, as lecturers we never got chalkboard 101 course like the teachers do. Hey, we just say, there's your chalk, you go right. Almost like a doctor. If anyone should get, never mind. Volts. Okay, so I've got my Thevenin impedance over there. So now I'm going to need space on the board again so that I can go and calculate the current that's flowing. But now, so Z Thevenin, I'm going to need it. So let's clear this out. So you've got that voltage there on your piece of paper. So remember, our final objective here is that P max equals half the magnitude of I squared times R. So IL then equals our V-Thevenin, which I just erased, the 65.96 angle minus 31.9 degrees, divide by Z-Thevenin plus RL. What was my Z-Thevenin? Now I'm gonna use it in rectangular form so that I can easily add the RL. So the 17.18 plus the 30 gives me a 47.18 plus, oh, it's a minus, sorry, minus J, let me just stand on this side, sorry, minus J 24.57. Right, so for you not to have to rewind, I'm just going to say again, so we substituted now, we're looking for the magnitude of I, so I need to calculate the current. What is the current? V-Thevenin, Z-Thevenin plus RL. So I'm just substituting my V-Thevenin in the top and Z-Thevenin plus RL. Here is my Z-Thevenin plus RL that I know is now 30 ohms. So the 30 plus the 17.18 gives me the 47.18, and the minus J 24.57, that stays the same. and you do the crunching, and you will get 1.24 angle minus 4.4 degrees amps. Hey, chalk. Yes, right. But I'm only looking for the magnitude. Hey, so I'm only interested in this 1.24 that needs to go into that. In other words, my Pmax equals a half 1.24 squared times, and was 30. So the maximum power I can actually get into that load is a mere 23.06 watts. Yeah, that's not impressive at all. 23.06 watts. Okay, that was practice problem 11.6, and lo and behold, that's all I want to do for this lecture. It's probably one of the shortest that you'll ever get. In the next lecture, we're going to move to an all-important topic, root mean square. So don't miss out on lecture 18. Chapter 11.4 it's going to be. All right, I'll see you in the next one. Bye-bye.